You have to know that. If you forget, I'll give it to you. That's not a big deal. You should know 5,280 feet, 1,760 yards. That's a common one. Just make sure you convert, because always be careful. This is in feet per second. This is in feet per second, and this is in miles per hour. It changed. Yes. Now my board is the strangest board. You know that. Some days it works perfectly. Other days it's crazy. So we adjust.
I plugged it in a calculator and I got like something completely different.
All right. So let's put this in your calculator.
Oh wait. Never mind.
You're good?
Yeah.
Anybody else struggling with this?
Wait, what did I say? You divided it by 16.6.
But if you're going from here, you're going from miles to you're going from 6 miles per hour. Okay, you want to get to feet per second. So remember, like in the old way you did it, you had to cross out the miles. How many feet in a mile? 5,280. And then you had to go cross out the hour. How many seconds in an hour? So you could go to minutes first, 60 times 60. So if you do this and you multiply these two things, these cross out your denominations. So you end up in feet per second. So 6 times 5,280 divided by 3,600. That'll get you your feet per second.
I actually lied. I didn't get the same thing.
You did it.
I got 400.03 and then 11.691.
You're fine. 400.03, that's close enough. You're close enough. I mean, try to get as close as you can. Give me your time. Always give me your time on this. If your equations are a little bit off, I can always go put your equations in, and it's easier for me if I have the timestamp. Then I go to value, I just look at that time and I see where you are. Rather than have to try to put yours in and then trace it. It's easier with the timestamp. And if they ask for when, then you have to. Will this be a home run? No, it does not clear the fence. If you come and you show me that at that time, close by 400 feet away, that he's not going to make it, just make sure you show me something. Don't just say yes or no. Okay?
On the test, are we going to have any where it was like the first lesson you did, you just like write out the table? But I like this.
Yes. I'm going to give you an easy one first to start, and then a couple like the conversions that come out like an ellipse. Something easy, or circle. I can give you a circle or an ellipse. I gave you number 4, right? Okay. Just to the Ferris wheel was so fun too, because if you do simultaneous 2 circles at the same time, 2 rotations, you kind of see where it hits, but it's a little bit more involved. So a baseball was thrown from the stands 32 feet. So someone's sitting in the stands 32 feet above the field. And if they're throwing, when they let it go, here's their angle of elevation right here with their horizontal. When and how far away will the ball strike the ground if the initial speed is 32 feet per second? So there's no other stipulations except the 32. Remember, anything vertical goes in the Y. Wind speed, that's horizontal movement, that goes in the X. So always start with your basics. Here's your basic. And then add and subtract whatever you need to do. So we're going to be 32 feet up. There's my plus 32. This one came out nice, and you could even take it out of your table, this one, right? When you hit the ground, you got a Y equals 0 on this one. So this is your horizontal distance. And that's what we're looking for. Remember, when you look for it to turn in your table, be careful you don't look at the X. The X will keep increasing. The Y is the one that's going to turn. Everybody okay with this one? All right. I didn't give you the shot put. The shot put was actually nice. It just was, you were 6.5 off the ground before your arm threw the shot put. So, I mean, it wasn't bad to do, but it's okay. A golf ball leaves the ground at a 30-degree angle at a speed of 90 feet per second. Will it clear a 30-foot tree that is in its way 135 feet down the fairway? So, you get your pieces over here. There's nothing extra to add. Golfing it off the ground. I want to trace until my X is 135 feet. Once my X gets here, I want to see what is my Y. Is my Y going to clear this tree? Is going to clear this tree. So when you get to this, you're very, very close. So you've got to get a little bit more exact. Remember the other day we were so far away? I think it was like 100 feet away or whatever. That I don't need, but this one you have to get very, very close to it. So get as close as you can to the X and give me your Y. I went a little bit over the X and looked at my Y. A little bit before, a little bit after, look at your Y if you can't get as exact. And it does not clear the 30-foot tree. Your ball just landed in the tree. So who says golfing is not math related? Okay. Questions on this? Can everybody do this? This is all you're going to see tomorrow.
Yeah.
Yeah.
Application?
Like this is an application.
No, we're gonna have more. That's when we
Oh, no, I'm sorry. You're also going to have the eliminate the parameters.
What?
Eliminate the parametrics, like make it a rectangle thing. Did I give you this one?
Yeah.
Okay. A golf ball is hit with an initial speed, blah, 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 from the tee to a green that is elevated 45 feet above the tee. So when they're hitting up a hill. So here's where the rise is, right here. Assuming that the pin, 369 feet down, doesn't get in the way, where will the ball land in relation to the pin? So the pin itself is 369 feet away, but you have an elevation here. So you're going to have to keep track of your Y. Is it to the left, to the before the pin, after the pin? If it's rising to the 45, it's before the pin. If it's coming down after the 45, it's after the pin. So we can see that it's coming down. The ball just passed, slightly past the pin. The pin is at 45. When Y is 45, if you can get close to this number, the X, you want to see where you are in relation to this. But when you get close to this, your Y is on the opposite side. It's just a little bit beyond it. So you don't hit your hole in one.
Why do you need that?
Why? Because it's up on a hill that you're hitting to. And the pin is just marking the hole to, for it to go in. So when you hit this ball, if you're 369 feet horizontally away, where are you vertically? So you're a little bit past the 45. So you're when you look at this, your hill goes like this, doesn't it? And it comes back down. So this is where your pin is at 45. If you're here at 45.1.7, you just passed it. You just went over it. If you were 44.999, you were just in front of it. Like, it has to be exactly there to get a hole in one. And you know how hard it must be to get a hole in one. Does this make sense? It just threw another little thing in here by giving you a rise to this. And that was it for these guys, or we had one more? That was it. Okay. Those were nice. Okay, my advice is, before you even eliminate anything, graph the two parametric equations and see what it looks like. Because that's going to tell you later what your rectangular equation is going to look like. So, rectangle is just xy. Because, when you do your parametrics, we get a time, we get an xy. We can only plot the xy. That's all you have on your grid, is xy. Yeah. So when we were just plotting an XY graph, we're just plotting an XY, you want to know what is I'm looking at. So when you graph that parametric, it's a parabola. So my parabola has many shapes, many forms for this, but this is one of them. Because we just got done with your conics. So therefore, I'm probably going to build something that looks like one of these. And if it's opening up or down, I'm hitting the x squared. If it's opening sideways like the next one, I'm hitting the y squared. So as you start solving this, it's going to look like that. So if it looks a little strange, it's going to be set up like your parabola formula.
Wait, so should the final equation be the y squared or the parabola?
In this case, it should be an x squared.
No, I mean like when you're like writing that, like y, like should like the final answer be y equals?
Y equals? No, you don't have to work the whole thing out. It probably looks better in the form that we just went through with your conics, because now from there I can see where it opens up. I can see the vertex. Like this is your vertex form, so I can tell my vertex. So by me looking at my vertex and me looking at this graph, I can absolutely see the 7, 2. I could see that this is positive. This is my 4p. My 4p is positive. It opens up. I don't care what p is, but my 4p is positive, so it opens up. So I know that I have the right equation, because that's going to help you out. Don't multiply the whole thing out and make it a quadratic, because then you really can't tell, is that the right one? Leave it in vertex form. We just got off your conics, so those are you're going to be visiting again. Mm-hmm. Yeah.
Y equals 1/2 x minus 7 squared plus 2.
Oh yeah, so what happened here?
This time you multiply it by 2. No, I think you multiply by 2.
Yesterday, did we have it on the right side? Oh, you know why? Because we had to have. I didn't put the x squared by itself.
Yeah, no, you didn't.
I didn't put the x squared by itself yesterday.
Yeah, I thought you were squaring it.
Yesterday when we did this, we just left it like this with the x squared in it, and we pulled out the x squared. The x squared should have been on the left-hand side. Because then you'll know that by this. This is a parabola opening up, so it's got to fit this format. Because you're going to graph those two.
Okay.
You're going to take, the first thing you need to do is just take that and go to your y equals and put this in. We graphed this yesterday so you could see it. Oops. I don't know what this looks like. I'm assuming when I put one into the other, if you're putting x into y, if you're putting x into this guy, there's your square. So a square says quadratic, right? Parabola. So I know I should be getting a parabola because I'm putting my x into my y, basically. So I'm keeping my square. So graph this before you start. I'm just doing some mistakes. Oh, I'm going to change that. Oops, I left out a point thing. Okay, so graph it. So I see a parabola. So isn't my format x, when it opens up, x minus h squared equals 4py minus k? That's what I want my final answer to look like. Yeah, yesterday I left it on the wrong side.
But where'd you get the 2 from? Like the coefficient?
So when we're here, like right here, yesterday I took out the 1/2, but I had to get the x squared to the other side. So just flip them around, and rather, you can't leave anything in front of here that has to be a 1. So just multiply it by 2. Get rid of your denominator. Just find a common denominator.
Is that a regular 2 or out formula?
No, this is just multiply this by 2. Multiply this by 2. Oh, it looks like I'm squaring it.
Okay.
Yeah.
Yeah, that's what I thought it was.
Sorry, no, I'm just multiplying by 2. If I put parentheses around the whole thing, then I'm just multiplying by 2. If you square, you got to square each part. Okay? So that right there, when I graph that, it's going to tell me what I'm going to find out at the very end. And the second one that we have, this one will help too. Watch, because this guy, if I graph this, now watch what happens. I'm putting my x squared into here. This is going to be a little bit different. This one's going to come out to be the y. So I graph this first. It's so important that you graph it and see what it's going to be. Otherwise, yeah, you're not going to recognize it when you're trying to build your equation. So here, now, I can see my y squared. See, your t-step's a little bit weird. You might want to make your t-step a little bit smaller. Make it a little smoother. Does it matter? Not really, because you're just looking to see what this is. So now I have a parabola, right? What's the format of my parabola? Y squared. So my parabola should say y squared now. Right away, before I even start, I'm just going to sketch this and say, oops, there's my parabola, and here's what I want it to be. Here's what I want it to be. So when I get here, I solve this guy for t. Remember, it's a positive or negative, but we're just dealing with the positive. So we'll take the square root, we'll substitute this into here. Now, here's the thing. If you square both sides, you have to isolate your radical. We did this a long time ago. Get rid of this 3. Bring this 3 here. Because if you would have squared this, you would have still ended up with a radical in the middle. So isolate your radical first. Move the 3 over. And by moving the 3 over, aren't we kind of building your parabola? Isn't the y supposed to be by itself over here? Isn't that y supposed to be squared over here? Because I'm sitting there looking at my formula, so I know what I'm going to expect. Get your 36. This is going to pop out. Reduce this down, and you got your equation. Now, put your calculator back into regular mode, sequential mode, and see if that graphs you the same thing. But you'll have to do it 2 times. You'll have to take the square root.
So like particular equations are graphed with like regular.
Yep. Yep.
Do you have to like reduce the 36?
Over 8? Yeah. Yeah. You have to reduce. You have to reduce everything. You have to always simplify your radicals, always reduce your fractions. The only thing we don't have to do is rationalize your fractions, the radicals in the denominator. You don't have to do that. We don't do that in precalc, just basically because you need those ratios with the radicals in them, so we don't rationalize. But everything else you have to reduce. Can everybody do this? Okay. Okay, this one, I see the sine and I see the cosine. Right away looking at this, I see 2 3. What is this going to be? Circle, they're both the same, right? So I pull out this one's easy, I'm going to build it like a rectangle. I'm going to build it like an ellipse first. So you're going to build it like an ellipse, but it's going to come out to be a circle. If you left it like this, it's not a big deal because a circle is a special kind of ellipse, like a square is a special rectangle. So if you want to get it into circle format, just multiply it by 9. Now I can pull out my center, I can pull out my radius. If I graph these two, the only thing when you graph that two, these two, what do you have to do to your t-step? If you graph this, you're going to have to send this into, make sure your degrees.
Or is it the center 0, 0?
The center 0, 0.
Yeah.
Sorry about that. Center 0, 0. Be careful on your t-step if you're doing this, because this, you need to go from 0 to 360. And you don't want to have a t-step of 0.3 because you'll be sitting there forever. So, and again, if you zoom 5, it'll look a little bit better. It'll take the distortion out. So as soon as you do that, you should know what you're looking at. Just, can everybody adjust their windows? And that one was kind of, not so bad because we can see the two coefficients. They're the same exact. Okay. This one's a little bit different, but because we see secant and tangent, we start with cosine squared plus sine squared equals 1. And we say, I need to get that word tangent in there. So I need to divide my sine by cosine squared to get tangent, right? So because it's an equation, I divide everybody by cosine squared. This is the one that you have to know. Everything else you can get from there. So there's my 1 plus tangent squared equals secant squared.
If you just like memorize the two equations, are you okay then?
You can memorize it, but you can always just memorize the 1. Yeah, memorize it. A nice way to memorize it, the T and the S go together because the two C's go together. The cotangent and the cosecant go together. And then just plug in what you have. Solve for secant, solve for tangent, and just plug it into this. Start like this first. Plug it into this. I get to here and I say, oh, I realize I have to set it equal to 1. So when I move this guy over, I take the opposite. I have a hyperbola. And if you graph this first, you get a hyperbola. And it graphs weird. It goes 1, 2, 3, 4. It graphs in weird times. Questions? No? These aren't so bad, right? Okay, so now I realize I've got something else going on, so I solve for cosine, I solve for sine, I use my one identity, I plug it in, and again, I have a circle. Because my two denominators are the same, I have a circle. And this right here, tell me that I have a circle. Okay. I pull out my center and my radius. Good? Yes?
Wasn't that equation cosine squared plus sine squared? Does the squared go on outside of the theta or simply the theta?
It goes when you put it in your calculator.
No, just like when you write that equation.
No, it goes by the cosine. You don't want to square your angle, you want to square your cosine of the angle. You lost?
Yeah, just put out.
You betcha over there? You betcha with the other side? You want to square your cosine, you don't want to square your angle. Okay, now, again, we can see your two coefficients are different. Don't worry about the double angle, just treat it like a regular angle. It's still an angle, and both angles have to be the same for you to do this, so that's fine. Convert it and plug it in. You have an ellipse. Do you have to write all that information? No. Give me the equation of the ellipse.
Didn't you say you were gonna give us a practice on say it looks like center?
The circle with the center? Yeah, was this the last one?
No, this was well, you said no to that one. Can you go back?
Yep.
Wait, no.
So here, want to do a circle one?
Sure.
Did we do the last one?
No, you said skip it.
I'll skip the last one. Okay, good. All right, so here, circle. Let's make the center be 4, -5, and the radius be 2.
Yeah, see, I don't know how to do this.
Okay, but you have to know these two. The x and the h go together. The x always goes with the cosine. So, if you struggle, I'll give this to you. Well, all right. But it's easy to remember because the x always goes with the h, the cosine always goes with the x.
Yeah. Wait, what is that?
That's the formula that you need to build your circle. We did this probably last week.
I remember doing it, I think. I don't think I really ever got
It's this Thursday. We probably did this a week ago. So then all you really have to do, this is your H and your K, and that's your R. You just got to plug them in.
Yeah, but then
Yeah, just plug them in. Let's do. And now you're okay to build your circle. Just like subtract, yeah, just do the same thing that you did before. The only thing you had to do was put them into this.
so now you just solve it.
Now you do the same thing. Subtract 4, divide by 2, add 5, divide by 2, and then just use your sine squared plus cosine squared. Once you get there, you just have to plug them into that. I would like you to know that, but if you struggle,
I think we can do it. We don't need the
So
formula.
now
wow, speak for yourself.
Wait, so now what?
Now you do your cosine squared equals sine squared.
Okay.
This is the only identity you have to know. And you've had to know this all through trace. Remember, okay, here, this is a good case in point here. Don't leave, even if this was an ellipse and they weren't the same, don't leave it like this. I want this bottom resolved. I want it to look like whether it's an ellipse or whether it's a circle, you can leave it to me like this. But I want the bottom, the denominator, resolved. Since it's a circle, just multiply everybody by 4 and give me the circle. This is your last. This is our last test. This is our last test. Huh?
So, if you were to give us a question like that, we can find the equation, you wouldn't have to go through all the steps, like, we just plug it into the x minus b squared.
You could, no, give it to me in the circle formula. No, I need you to go through this. Yeah. Yeah, I get that it'll fit into your circle formula, you know, your x minus h thing, but I want you to do it parametrically.
We don't have any more units?
You have one little unit. We have a polar yet to do. We have polar, which